Okay. By the end of this class, you'll be able to describe the difference between static and kinetic friction, solve problems that incorporate coefficient of friction. All right, so let's say we got this lab table I've turned upside down. It's a chunk, okay? And I'm going to try to push on it to slide it, okay? So I'm going to sit here and go, oh, man, it's pretty heavy. All right, so I want you to draw the free body diagram of me pushing on the table and do the setup. We're going to assume that I'm pushing horizontally. Okay. Go ahead and do the sum of the forces in the x and y direction if you haven't already, but set it up completely. All right. So, how do we do? Good. All right. So, there's our setup. Let's put some numbers to it. We have a disturbed bunch of children out there. Goodness. All right. So let's say when I push on this, I push with 100 newtons of force. How much friction is present? 100 newtons. Good with that? Like, all right. Push at 200 newtons. How much friction was present? 200, like 300 newtons of force. Friction is 300. What's happening to friction? It's going up. It's increasing. Okay? So as I push harder and harder and harder, friction is counteracting me, pushing harder and harder and harder back. Okay? This is known as static friction. This is the friction present there is no slipping or sliding between surfaces. Static friction is when there's no slipping or sliding between surfaces. Okay. Now, where does friction come from? What we're going to do is we're going to like zoom in to this interaction between the box and the floor. Kind of like Google Earth it, zoom in at a molecular level. So we're zooming in. This is the surface of the bottom of the box. This is the surface of the floor at a molecular level. It's not smooth. It's pretty rough at a molecular level. Okay? So, do you see where friction comes from? You got the mountaintops of the box and the valleys of the floor interlocking. And as I push on the table or the box, it's like, does that make sense? Where friction's coming from? At some point, I can like own it, and it's like, all right, yeah. Okay. What's happening at a molecular level once it starts sliding? I'll tell you. So you're pushing harder and harder and harder on that. At some point, the mountaintops break. Right before they break, this is known as maximum static friction. Okay, we've maxed it out. Okay, and if you exceed that, if you push harder than maximum static friction can push back, then all of a sudden you're like, and you totally just decimate the mountaintops. Okay, if you listen carefully as something slides, you can hear the screams of all the villagers in all the microscopic towns, like as their land is like, and just mass chaos. Okay, this is what causes your tennis shoes to wear off over time. Does that make sense? Like you're leaving chunks of mountaintops of your tennis shoe behind every time there's any type of slipping or sliding between the surface of your shoe and the floor. This is why you have to change your tires every 50,000 miles or something. Does that make sense? Where that's coming from? Just no, give me something. Okay. All right. So, this it reaches a max. This is the breakaway point. This is maximum static friction. This is just before it starts to slip or slide. Just before it starts to slip or slide is maximum static friction. After that, it starts to slide. This is known as kinetic friction. This is the friction present when surfaces are slipping or sliding. So friction present when surfaces are slipping or sliding. Now, a couple characteristics that I want to point out. Number one, why'd you make it squiggly? That's because the microscopic landscape of the floor and the box is not necessarily uniform. Sometimes you might be going through the Himalayas. Other times you might be going across Kansas. Like, it changes. So there's a little bit of variation. We'll consider it fairly constant, but just so you know, there's some imperfections in the surfaces. Okay, are not uniform. Second thing I want you to notice is we dropped how strong the friction is. Okay, I want you to imagine back to when you were pushing on something really heavy, trying to like get it to start sliding. Once you got it to slide, was it a little easier to keep it going? Why do you think that is? I know you have some thoughts. Inertia is one of those reasons. Okay. Once you get it moving, it just wants to continue moving. Okay. The second reason is once you've broken through like that initial break, then the mountaintops and valleys don't settle all the way back down. They're like skipping across the mountaintops. Okay. So kinetic friction is going to be less than your maximum static friction. Okay. Good with that? Now, there is an equation associated with friction, and that is this. Friction is equal to the coefficient times normal force. This is a Greek letter mu. You can make it with a lowercase u with a stick in front of it. Okay. This is the coefficient of coefficient of friction okay. This describes how rough the surface is. Okay. How rough the surface is. Different surfaces have different amounts of friction. Okay. When you were growing up, my assumption is you found some really good combination of socks or pajamas or something that allowed you to run and slide on some type of floor and like Shit. Right? Okay. If you try to go and do that on concrete, it's like, boom. Like, oh. Okay. Some surfaces are slipperier than others. That's what the coefficient of friction communicates. Okay. And then it says it's dependent upon normal force. That's kind of weird. Okay, so which do you think is going to be easier to slide, this recycling box or this lab table? Recycling box. Good job. Thanks, guys. Man, it's painful. It's like, I know you know the answer. Why? Why is the recycling box going to be easier to slide? It's lighter, weighs less. Okay? See? Okay. Now, so you might say it's dependent on the force of gravity. However, what is the object that causes normal force? What's putting normal force on the box? The surface of the ground. Okay. What it's looking at, what the normal force is looking at, is how hard the mountaintops and the valleys are being squished together. Okay. The more this weighs, the greater the normal force, typically. Does that make sense? Okay. But it's actually, normal force is a better descriptor, describes better what happens between the mountaintops and the valleys. Okay. Good with that? So we've got an equation, actually two different equations, but they have the same format. One is for maximum static friction, and you have the coefficient of static friction, and the other one is for kinetic friction, and you have the coefficient of kinetic friction. It's the same format, but the coefficient of static friction is different than the coefficient of kinetic friction. Okay, so I'll give you both of those on a test. Okay, so that's the background knowledge. Let's see how we can apply it. Okay, so let's say in my example, my box is, let's say it has a mass of, oh, that seems really heavy. It is, yeah, pretty heavy. Let's say 100 kilograms box. Okay, and I'm pushing with 350 newtons. And what I want to know is, I want to know what is the coefficient of static friction. That's what I'm in search of. That's what my question says. Like, hey, what is the coefficient of static friction? Okay. So I'm going to, so in problems, if it says, hey, it's just about to start sliding, or it's just began to start moving, or like, how far can this, or like, how strong can this force go before things happen? If there's any type of like just about, or just began to happen, that screams you're at maximum static friction. Okay, that's the buzzwords. Those are the buzzwords you're looking for. Say, oh, I've got maximum static friction. Okay. So I'm going to tweak this setup just a tad bit and put maximum static friction. So from here, you've already told me these things. I know that maximum static friction is equal to 350 newtons. Good with that? Okay. But I'm looking for the coefficient of static friction. Anytime they ask for the coefficient or they give you the coefficient of friction, and 95% of the time, you're going to be incorporating this equation. Okay, this is the only place you're going to see the coefficient of friction in an equation. They might just throw it out there to be a distractor, but usually you're going to incorporate that. So I need to use this equation. I've got 350, but now what do I need? Normal force. Where are we going to find normal force? When I was alluding to the fact that you need both the X and the Y set up, this is where. Okay. So I need to figure out normal force. Can I, like, all right, so find normal force in the Y direction. I've got 100 kilograms. Can I plug that in there? Nope. What do I need to do first? Yep, plug it into force gravity is equal to mass times 9.8. So we've got 100 kilograms times 9.8. Find that to be 980 newtons. So I can find the normal force in this case is also equal to 980 newtons. And plug that in there. So we got 350 is equal to coefficient times 980. So I find the coefficient to be equal to 0.357. Okay. Your coefficients don't have a unit. They're unitless. It's just a ratio of forces. Okay. They're usually going to be less than 1. It's not illegal, but most interactions are less than 1. Okay. Do not be surprised if it's a decimal, like a point something. Like that's kind of what you're expecting. Okay. If you're like on tape, that's going to be over 1. Something like that. But most surfaces. Okay. Sound good? So you got a worksheet that's due on Tuesday. Here's my strong, overwhelming suggestion. Set it up and be organized. There are a lot of moving parts. Okay. And you got to keep track of it all. Okay. You can do this. This is not hard math. You just have to like use your setup as your roadmap. Okay.